So in this study, convolutional neural networks were used. And so I did want to share this article that was published by the National Institute of Standards and Technology. So in the past, a lot of people have said that neural networks have a bias against African Americans. And so that's been supported by pretty much a few studies, but in this article they mentioned the MIT gender shade study and then the ACLU Congress study. And so in the MIT gender shades, this article kind of explains that while MIT reported that the neural networks were not able to accurately identify the faces of African Americans, what their test actually did was they were supposed to test demographic labeling, which is not the same thing as facial recognition. And then on top of that, when they actually replicated their study, they had different results, and it's supposed to. It is said that was due to kind of the change in the technology. And then in terms of the ACLU Congress study, they had 250,000 images of Congress members, and then they claimed that when they tried to do facial recognition on the African American members of Congress, that those were more commonly wrong. And so what actually happened in that study is that the the neural network would output a confidence level, and in that case, it was actually that the confidence level of the African American people that the software had missed were just a lower confidence level. So, but yeah, overall, by using convolutional neural networks, the NIST noticed that for the top of 150 algorithms, over 99% of them are accurate across both male and female and across African American and white demographics. On top of that, they noticed that for the top 20 algorithms, the accuracy between the lowest demographic and the highest demographic was 99.7 to 99.8%. And so in that case, it shows that there's not really any bias in terms of the actual neural network itself. So in my experiment, I used the Yale Extended Database. So this features 38 subjects and it has about 2,141 images. And so pretty much each subject has about 64 pictures. And what this, and then each picture is slightly different in terms of the lighting conditions or their pose, and so there's a lot of variation across all 64 images. And so my main goal was to be able to maximize accuracy while decreasing the computation time. And so the way I did that is I started off with a kind of benchline convolutional neural network, and then I iteratively changed different parameters of that to be able to decrease my time and maximize my accuracy. So what I ended up getting was pretty much I was able to get across my data sets a 100% accuracy, and then I was able to pretty much bring my time down from 1,950 seconds down to 71 seconds, and so that is a approximately 95% decrease in time. And this was really interesting for me to see that you can do the same thing and have it just be way quicker. So some of the different parameters that I changed were, for example, just different aspects of the convolution layer. So how many filters it had, um, the stride side, the kernel side, same thing for pooling layer. And then I was also able to change the number of hidden layers and number of nodes. Um, and yeah, so overall, I mean, these results are good, and this study is kind of should be. I mean, in terms of my study, it is successful. However, it should also be noted that if you looked at the images on the previous slide, the images are fairly simple, so they're very small, which helps kind of keep a processing time pretty quick. On top of that, the fact that they're cropped makes it a lot easier. There's not a lot of noise or I guess distractions in the pictures. None of them also have any accessories such as glasses, face masks, all that. So the data set that I had was definitely much more on the simplistic side. And that definitely has a very big importance to this because especially compared to other studies, I mean, my data, because I only had about 2,000 pictures, my data set was relatively small. But this was definitely at least a very good introduction into facial recognition. And I mean, some of the things that I would want to kind of continue on this would be, first of all, kind of expanding the data set and maybe even making my own. That way I can kind of just get as many different combinations as possible. Just, I mean, again, like this one, different lighting and different poses, but also what happens if you have a slightly different background, if you just different, kind of your hair is styled a little differently. So there's just so many things that they can kind of go to this, and the neural networks, the convolutional neural networks, are just so great to use for this because you just need just a lot of data, and then you'll be able to tune the layers and data recognitions. The hidden layers and the actual kind of feature extraction portion of it. Yeah, so now I kind of want to share the actual code itself. And so just to kind of, just to explain it. So the first part is just, if the files haven't been read yet, then the first thing is they just get, I find the directory, they get initialized and get read into the, as variables. And then from there I can also create the labels. And then at that point I'm able to normalize it. For this, I've saved the actual images and the labels to make the code run faster, so I just load in the images and labels. I end up splitting the data, so I did a 9 to 10 split, so my test size is 10% of my images. I know that this is a bit of a low number, but my kind of idea between that was, first of all, I don't have a lot of training data and I want to kind of maximize that. The other thing is that, ideally, when we do facial recognition, at least when we think about it into day-to-day life, it's usually more on the sample size of one test sample, because it's like, for example, on a phone, is this me? Or is this the owner of this phone? So that's why I felt like for this particular situation, this was appropriate. And then kind of this is where the magic happens in terms of the actual convolutional neural network. So I'm just gonna run it. And so this is the way I'm going to be running it now is kind of what it is in its most optimal state, and it takes about 71 seconds to complete. Yeah. So I'm just going to let it run just so you can see that the first kind of epoch is done, and then after that I'll just go ahead and just cut straight to the end. So the algorithm has finished running, and as we can see, we were able to get our 10 pokes. This one took a little bit longer to run, and we see that the validation accuracy is only 99.6. But overall, the algorithm works well, but it is definitely missing just a larger data set, and so I'm pretty excited that I have the opportunity to learn this stuff, and I'm definitely looking forward to being able to kind of expand on this project because I had a really good time doing it. All right. Well, thank you so much for joining me, and